Welcome back, and we're going to take a look at example number 3, which is about reasoning to establish the equivalence of two lines. So what does the equivalence of two lines mean? We're going to take a look at a couple of equations. So if we have the equations y equals 2x plus 3, or negative y equals negative 2x minus 3, or 5y equals 10x plus 15, and we graph all these three equations on the same grid, we'll see that we will obtain the same graph. So the same graph can be presented or represented by different equations. So in this case, we say that these equations are equivalent because they produce equivalent lines or same lines. So we're going to take a look at example 3a, where we're given the equations of two lines. This time they're in vector form, and just like the equations when they're given in scalar form, when they are in vector form, we can produce different equations that graphically represent same line. So how can we tell whether or not the two equations will represent the same line? Fact number 1. If two lines are the same, they should go in the same direction. For example, this line and this line here, two different lines, they must be parallel to each other. So what guarantees that two lines are parallel to each other? Their direction vectors. So the direction vector of this line, which can be this one, for example, and the direction vector of this line, which can be this one here, for example, must be scalar multiples of each other. So I'm going to call this M1 and this one M2. So two lines are going in the same direction if they are scalar multiples of each other. Now, another condition, so the second condition that must be fulfilled for two lines to be equivalent, though, is not just the direction, but they must be or must have a same, at least a common point. And obviously, if they have one common point, they will have the rest of the points the same because they're going in the same direction. So we're going to say common point. So two things that we need to keep in mind when we are proving the equivalency of the lines. And I'm going to start with the direction vectors. So the first direction vector, I'm going to call it M1, has the coordinates negative 1, 2, and 5. Direction vector M2 has the coordinates negative 2, 4, and 10. You can obviously see here right away, but I'm going to go through the process of how we can check whether two vectors go in the same direction. So I would compare the x coordinates together by simply finding the ratio. So you have negative 2 over negative 1 for the x coordinates, which equals 2. For the y coordinates, we have 4 and 2. So we're going to go 4 divided by 2 again is 2. And for the last coordinate z, we have 10 and 5. So we have 10 over 5 equals 2. So as you can see here, we have 1, 2, 3 ratios of the respective coordinates that produce the same scalar. And that tells us that, so remember this was M2. So M2 seems to be bigger, right? So we're going to say that vector M2 equals twice vector M1. And this is enough for us to prove that the two lines L1 and L2 are parallel. Now, the next condition that must be fulfilled is that the lines have a common point. And now I'm thinking, let's take a look at both of them. Is there any point that is visible in the equation of each line? So you see that we have a starting point here and a starting point here, which means that if either of these points is common, that means that the lines are equivalent. So what that means is that we can take the coordinates of this point and substitute it into the equation of the first line. So the starting point of the second line, substitute in the first line and see if it satisfies the equation. Or we can take the coordinates of the starting point of the first line and substitute it for any point x, y, z in the second line and see if it satisfies the equation. And if it does, it means that the point that belongs to line L2 fits into line L1, so it's common, and vice versa again. So what I'm going to do is I'm going to use the point for negative 10, negative 21, and I would substitute this as a point on the line L1 to see if it fits. So we have negative 1, 0, 4. That's the starting point of this line. And then I will add the vector, which is S, negative 1, 2, 5, the direction vector. So if this point fits into this line, then we'll be able to find the same multiplier S for each and every coordinate. So using parametric equations, you will have 4 equals negative 1 plus negative 1s. So this negative 1 here plus s times negative 1. So 4 equals negative 1 minus s. So s would equal negative 5. Next, we're going to check the y coordinates. So negative 10 equals 0 plus 2s. So negative 10 equals 2s, which means that s must be negative 5. So far, the multiplier s equals negative 5 is working for x and y. Let's check and see if it works for z as well. So to work for z, we need negative 21 to equal 4 plus s times 5. So 4 plus 5s. So that would be negative 25 equals 5s, which will give the s value of negative 5. So as you can see, the same multiplier would work to satisfy or to have all the coordinates fit into the equation. So that means that the lines L1 and L2 will have a common, at least one common point. So one common point. And two parallel lines means that we have the same line. So that's how you prove it, and that's the end of it. So in the next example, we have again the similar situation, and we have to check and see if the two lines are coincident or not, or are equivalent or not. Again, we're going to start off with the direction vector. So direction vector M1 here is negative 1, 1, and 2. Direction vector M2 here is 1 half, negative half, and negative 1. So we'll compare the direction vectors, and we'll say that M1 over M2 would be equal to negative 1, 1, 2 over a half, negative half, and negative 1. So again, the same strategy. So we can compare the x's and then the y's and then the z's. So we'll just find the ratios. So that would be negative 1 over negative a half equals 2. Next, 1 over negative a half. By the way, that's negative 2. So 1 over negative half, that's a negative 2. And 2 over negative 1 is also negative 2. Now, obviously, very often, you'll be able to tell right away what the multiplier is, but I'm just going the long way here just in case we deal with numbers that are a little bit more funny looking, like fractions, like 23 over 7, for example. So since we obtained the same multipliers, right, or same ratios, then we are going to say that the lines M1 and M2 are collinear, because it seems that line M1 equals negative 2, the vector M2. So they have the same direction. How about a common point? So for a common point, now we're going to substitute the coordinates of either starting point into the other equation. So I'm going to choose this time 1, 6, and 1, which is the starting point of the first line given, into the second line here. So we have -3, 10, and 12, and then plus k, 1/2, -1/2, and -1. So in this case, we must have 1 equals -3 plus half k, 6 equals 10 minus half k, and 1 equals 12 minus k. So we're going to solve the equation. So 1 minus 3, that's a 4, equals half k, which will give a k value of 8. 6 minus 10, that's -4, equals -half k. So that will give a k value of 8. So far so good. It looks like they would fit in. And last we have 1 minus 12, that's -11, equals -k, which makes k equal to 11. And that would be the deal breaker, because yes, these two k values are equal, but they're different than the third one. So the z coordinate is not going to fit in, which means that this point here won't fit into the equation, which means that the lines are not coincident. So L1 and L2 are different lines. Well, thank you for watching, and then we'll continue with the rest of the examples in the next video. Bye for now.